All right, class, let's settle in. Now, I know what you might be thinking. The Pythagorean Theorem? Seriously? We all learned that back in middle school. But I want you to just push that textbook version out of your mind for a bit. Today, we're going to look at this ancient rule not as some dusty old formula, but as a living, breathing idea. An idea with a secret history, a beautiful wordless logic, and a future that stretches into dimensions you probably haven't even considered. And it all starts with a simple question about gold.
So let me pose a thought experiment from the mathematician R. Smulian. Picture a right-angled triangle, and on each of its three sides, imagine we've built a perfect square. Now let's say these squares are made of pure beaten gold. You get a choice. You can take the one large square that's sitting on the longest side, the hypotenuse. Or you can take the two smaller squares from the other two sides.
So what's it going to be? The one big payday or the two smaller ones? You know, when Professor Smulian actually asked his students this, the room was split, pretty much right down the middle. It's one of those questions that really messes with our intuition about size and value.
And here is the absolutely beautiful and kind of surprising answer. It makes no difference at all. The value is exactly the same. The area of those two smaller squares is identical to the area of the one large square. And that right there isn't just a clever brain teaser. That is the Pythagorean theorem. Not as an equation, but as a physical, tangible truth about the world.
Now, this incredibly powerful idea has been with us for a very, very long time. But where it actually comes from, well, that story's a little more complicated than the name suggests. So let's do a little digging.
First things first, here's the official version we all had to memorize, right? For any right-angled triangle, you take the square of side A, add it to the square of side B, and it will always equal the square of the hypotenuse, C. Simple, clean, and unbelievably useful for everything from building a house to calculating trajectories in physics. It's really a cornerstone of our world.
The name on the tin seems to give it all away. Pythagoras, of course. But, as it so often goes with history, the real story is a bit messier, and honestly, a lot more interesting.
Okay, just look at this timeline. It tells a pretty shocking story. Archaeologists have dug up Babylonian clay tablets dating back to almost 2000 BC that straight up describe this exact mathematical relationship. We're talking more than 1,000 years before Pythagoras was even born. The idea was clearly out there, in use, long before the Greeks got a hold of it.
So here's the bottom line. Pythagoras probably didn't discover the theorem at all. What he was, most likely, was a brilliant popularizer, a genius at marketing the idea, maybe proving it in a new way, and building a whole school of thought around it. Think of him less as the inventor and more as the world's first great mathematical influencer. He made it famous.
So if the theorem is that old, how do we really know it's true? Well, there are literally hundreds of proofs out there, but I want to show you one of my absolute favorites. It doesn't use any algebra, no numbers, just your own two eyes. It's what we call a proof without words.
Okay, let's start with our diagram again. I want you to look really closely at the biggest square, the one on the hypotenuse. See how it's been cut up into a bunch of smaller, colored shapes and triangles? Just think of them as puzzle pieces for a second. The total area of all those little pieces is, obviously, the area of that big square.
And now for the magic. Watch what happens when we just slide those exact same pieces around. We don't change their size, we don't change their shape, we just rearrange them. And look at that. The very same pieces that perfectly filled the big square now perfectly fill the two smaller squares.
The area has to be the same, right? We didn't add anything, we didn't take anything away. So the area of the large square must be equal to the total area of the two smaller ones. It's just so elegant. It's a profound mathematical truth that you don't calculate. You just see it. You witness it.
Okay, so far we've been playing around in the nice, flat, two-dimensional world of a blackboard. But we don't live on a blackboard. We live in a three-dimensional world, which leads to a really fascinating question. What happens to this theorem when we drag it out of the flat plane and into 3D space?
So to get to 3 dimensions, we actually have to take a step back first, all the way down to 1 dimension, a single line. In 1D, the theorem is almost laughably simple. It's just adding lengths together. Line segment x plus line segment y equals the total length z. That's it. That's our starting point. So how do we get from that simple 1D line to the 2D theorem we all know? It's a two-step recipe. First, we take one of those segments, x, and we rotate it 90 degrees. Boom, we've created a right-angled triangle.
Step 2, we take every line in that picture and extrude it. We pull it straight out into the next dimension, forming a square. And just like that, x plus y equals z transforms into a squared plus b squared equals c squared.
Now here is where it gets really fun. What if we run that same playbook again? What if we take our entire 2D theorem as the starting point and apply those exact same 2 steps? We rotate one of the squares 90 degrees into the third dimension, and then we extrude everything. What shapes do you think govern the 3D version? Your gut instinct is probably screaming, cubes, right? Well, the universe is a little more creative than that.
The shapes that govern the 3D version of the Pythagorean theorem are not cubes, they're octahedrons, those amazing 8-faced diamond-like shapes. So in the same way that the areas of the 2 small squares add up to the area of the big one in 2D, the volumes of 2 small octahedrons add up to the volume of the big one in 3D. How cool is that? It's a totally fantastic and non-obvious leap.
So, we've gone from ancient Babylon all the way into 3-dimensional space. You might be thinking, okay, surely the story has to end there. But this theorem, it's not some relic in a museum. It is still evolving. It's still inspiring new math right now, today.
Take a look at this. It's a generalization from the computer scientist Edgar Dijkstra. Now, don't let the symbols freak you out. At its heart, this is a comparison. On the left, you've got a relationship between the triangle's angles. On the right, a relationship between its side lengths. Dijkstra proved that for any triangle, not just right-angled ones, these 2 sides will always have the same sign. They'll both be positive, both be negative, or both be 0. And guess what the special case is where both sides are exactly 0? Yep, that's our good old Pythagorean theorem.
And this is really why this all matters. It goes to show that even the most basic ideas in math aren't just closed, finished books. They are active, dynamic fields of exploration. They're like doorways that open up into much bigger, much more beautiful mathematical landscapes.
Which, of course, brings us to one final huge question. We've watched this theorem evolve from 1 dimension to 2, and then from 2 dimensions to 3. This pattern, this evolution, it just begs the question, is all of this just a shadow of an even bigger, grander theorem? A single, beautiful principle that connects all of these dimensions and maybe even higher ones we can't see? We don't have the answer. And you know what? That's what makes this so exciting.